Thanks to the organizers for this opportunity to present my work at ICECA. Today I'll be talking about subspace profiles, q-Whittaker functions, and Krylov subspace methods. So let Fq be a finite field with q elements, and suppose delta is a square matrix over Fq. We say that a subspace W of Fqn has delta profile mu, sequence mu1, mu2, and so on. The dimension of W is mu1. The dimension of W plus delta W is mu1 plus mu2, and so on. Now one can show that these muj's are weakly decreasing, and so mu is an integer partition of size at most n. For instance, if W is invariant of dimension m, then it can be seen that its profile is simply m followed by a sequence of zeros, which we think of as the integer partition with a single part equal to m. On the other hand, if delta is cyclic in the sense that its minimal and characteristic polynomials coincide, and if one takes a one-dimensional subspace spanned by a delta cyclic vector, then that subspace has profile all paths equal to 1. Let nq choose k denote the number of k-dimensional subspaces of Fq to the n. Given mu and delta, let sigma mu delta denote the number of subspaces which have delta profile mu. Bender, Coley, Robbins, and Ramsey pose the following problem. If I'm given this integer partition mu and the matrix delta, then determine sigma mu delta. In the case where delta is regular nilpotent, so nilpotent with one-dimensional null space, they showed that sigma mu delta is given by a nice product formula. Another case where delta is simple, so it has irreducible characteristic polynomial, they showed that sigma mu delta is again given by a nice product formula. They remarked that these two product formulas do not seem to have any nice combinatorial interpretation. To present a general solution to this counting problem, we will require some basic facts about symmetric functions. So let Qt denote the field of rational functions in T, and let's write lambda Qt for the algebra of formal symmetric functions in infinitely many variables. X is x1, x2, and so on. So we think of these symmetric functions as formal power series, which are invariant under interchanging two variables. And this algebra has many bases, namely the monomial symmetric functions, power sum, complete homogeneous, and elementary symmetric functions. It also has the Hall-Littlewood basis, p lambda, which depends on a parameter. So lambda Qt comes equipped with a bilinear form called the Hall scalar product, which is defined by the property that the monomial and homogeneous bases are dual. So here delta lambda mu denotes the Kronecker delta, which is 1 if lambda equals mu and 0 otherwise. There is also an involutory automorphism omega on lambda Qt, and it can be defined by requiring that omega on E lambda gives us H lambda. We'll associate a symmetric function to each square matrix, which will encode various enumerative properties of chains in its invariant subspace lattice. So recall that W is delta invariant if delta maps W to itself. So let alpha be a weak composition of n. So here the alpha I are non-negative integers with some n. Let x alpha delta denote the number of flags of delta invariant subspaces such that the quotient of two successive subspaces has a dimension given by the alpha I. For instance, if we look at x412, then we are looking at flags W of invariant subspaces W0 up to W3 such that all of the Wi are invariant and the dimension of W1 is 4 while the dimension of W2 is 5. The invariant flag generating function of delta is then the formal power series, where the coefficient of x to the alpha is simply these number of delta invariant flags of type alpha. Here the sum is over all inequivalent weak compositions. So two compositions are equivalent if one can be obtained from the other by padding a sequence of zeros at the end. Now, by using the fact that the lattice of invariant subspaces is self-dual, it can be seen that these x alpha deltas depend only upon the partition that is obtained by sorting the parts of the weak composition alpha. So using this, one can write this invariant flag generating function f delta x as a linear combination of monomial symmetric functions. And this shows that f delta x is symmetric. Let's look at some examples of invariant flag generating functions. So suppose delta has irreducible characteristic polynomial. In this case, the only delta invariant subspaces are the zero subspace and all of fqn. So the invariant flags have to be one of the lines in the sequence. And it's easy to see that the contribution in the first case is simply x1 to the n. Similarly, in the second case, it's x2 to the n and so on. So in this case, the invariant flag generating function is simply the power sum symmetric function. Now suppose delta is regular nilpotent. So nilpotent with one-dimensional null space. We could think of delta as a Jordan block of size n. In this case, there is just one delta invariant subspace of each dimension. And by using this fact, it can be seen that f delta x is simply the complete homogeneous symmetric function. Now the lattice of invariant subspaces of delta is actually a product of the invariant subspace lattices corresponding to its primary paths. So using this fact, one can see that f delta is simply a product over the primary components. And using this fact, one can show that the power sum and the complete homogeneous symmetric functions also arise as invariant flag generating functions. Here, regular means that the minimal and characteristic polynomials coincide. Semi-simple means diagonalizable over the algebraic closure. And split means that the characteristic polynomial splits into linear factors over fq. The next question of interest is what is the invariant flag generating function for a nilpotent matrix? Each basis of symmetric functions has a corresponding dual basis. So let h mu be the dual of the Hall-Littlewood p basis and define the modified Hall-Littlewood symmetric functions by using the following equation in terms of the transformed Hall-Littlewood functions. And then we have the result that the invariant flag generating function of a nilpotent matrix with Jordan form partition lambda is simply this modified Hall-Littlewood symmetric function evaluated at q. So the action of delta on fqn turns it into a module over the polynomial ring. By the structure theorem for finitely generated modules over a principal ideal domain, this module is isomorphic to a direct sum as shown. Here the gi's are distinct irreducible polynomials and the lambda i's are integer partitions. So with this in hand, one can describe the invariant flag generating function for an arbitrary matrix. So it turns out that it's given by this product of modified Hall-Littlewood functions. Here the inner square brackets denote plethistic substitution. We can use the invariant flag generating function to give a general solution to the problem posed by Bender, Coley, Robbins, and Ramsey. So here is a quick recap of their main problem. And here is the result. So it turns out that the number of subspaces with delta profile mu is up to sine and powers of q is given by a scalar product of two symmetric functions, the first being the invariant flag generating function and the second being a product of a dual Whittaker function w tilde mu which is defined as the omega involution on the Hall-Littlewood P function indexed by the conjugate of lambda, and a complete homogeneous symmetric function. Thanks to a result of LaSalle and Schlosser, one knows the complete homogeneous expansion of these W tildes, and so this theorem gives an explicit formula for sigma mu delta. In the case where mu is a partition of the ambient dimension, the theorem simplifies to give a nice scalar product for sigma mu delta. And the q-Whittaker functions are simply the duals of these W tildes as we have defined them. And this corollary leads to some finite field interpretations for some q-Whittaker expansions. For instance, the formulas given by Bender, Coley, Robbins, and Ramsey in the regular nilpotent and in the simple case simply correspond to these expansions of the homogeneous symmetric function and the power sum symmetric function in the Whittaker basis. Krylov subspace methods are a class of algorithms used to solve large sparse linear systems. This slide gives a historical overview of some contexts where these algorithms were used. But these methods have applications in many mathematical areas, including quadrature methods, the analytic theory of continued fractions, expansions of infinite series, orthogonalization algorithms, and also in quantum mechanics. For instance, the number field sieve, an algorithm for factorizing large integers that relies on such methods. Another example is Wiedemann's algorithm, which is used to determine minimal polynomials of large matrices over finite fields. So here is an application of the previous results to Krylov subspace methods. So as before, let delta be a matrix and let S be a subset of k vectors in FQN. The truncated Krylov subspace of order L generated by S is defined to be the space of all linear combinations of these VIs, where these FIs are polynomials over FQ with degree at most L. Let's define psi KL to be the probability that if we select a random tuple V1 to Vk, that the Krylov subspace spanned by them is all of FQN. So estimating this probability is crucial for analyzing these Krylov subspace methods. Brent, Gao, and Lauder posed the problem of determining this probability, or at least finding good bounds on this psi KL. Here is an excerpt from their paper. Using our results, we can show that this psi KL is given by a scalar product of the invariant flag generating function of delta with another symmetric function, which can be expressed in this W tilde basis.